So, have we found it? Have we actually found a sign of alien life? That is the million-dollar question swirling around a distant planet called K2-18b. You see, scientists have spotted a gas over there that, here on our world, is pretty much only made by living things. But is this the real deal, the breakthrough we've all been waiting for? Or is it just another false alarm in our very long search for company in the cosmos?
When headlines like this one dropped, they hit hard. Imagine that, a gas found on a world 124 light-years from here that on Earth is almost exclusively a product of life. For the scientists who spend their entire careers hunting for extraterrestrials, this wasn't just another headline. This was the exact kind of signal they've been listening for.
But let's be honest, right? We've kind of been down this road before. You remember the headlines? Proxima Centauri b, the whole TRAPPIST-1 system, that so-called super-Earth, Kepler 452b. It feels like every few years a new habitable planet contender pops up, only for the evidence to kind of fall apart under a closer look. So the big question is, what makes K2-18b any different? Is this the one, or is it just the latest hype?
So in this explainer, we're going to put you in the jury box. I'm going to walk you through all the evidence piece by piece. We'll cover the discovery, the super strange nature of this planet, and of course, the controversial molecule that's at the very heart of this mystery. You'll get the facts, and then you can decide for yourself, is the case for life on K2-18b a compelling one? Our story doesn't actually start with a planet. It starts with the machine that was built to find it. Launched way back in 2009, the Kepler Space Telescope was an absolute game-changer. Think of it like a cosmic detective with one single, all-consuming mission. Kepler's job was to find planets by watching for the tiniest dip in a star's light as a world passed in front of it. But then, in 2013, disaster strikes. A critical failure in its steering system nearly killed the entire mission. But in this incredible feat of engineering, the team figured out how to use the gentle push of sunlight itself to get the telescope stable again. This revived mission, which they called K2, then turned its eyes to a brand new target, red dwarf stars. And bam! Just 1 year into its new life, K2 hit the jackpot. It spotted a planet circling a red dwarf star 124 light-years away. Since it was the second planet found orbiting the star K2-18, it got the name K2-18b. The detective had found its prime suspect.
But you know, finding the planet, that was just step one. The real mystery started when scientists tried to figure out, what is this thing? It just didn't fit into any of the neat little boxes we have for planets. Okay, so this is where it starts to get really weird. K2-18b is about 2.5 times wider than Earth, but it's only about 8.5 times heavier. Now, if it was just a big rock, like a scaled-up Earth, it should be way, way more massive. This low density told scientists it wasn't a super-Earth, but it wasn't a gas giant like Jupiter either. And this led to a pretty wild new idea. What if it's a water world? A planet with a rocky core that's covered by a massive, deep ocean.
Okay, a water world, great. But hold on, here's the first big puzzle. Based on how far it is from its dim little star, the planet's average temperature should be around -8 degrees Celsius. At that temperature, any ocean would just be a solid block of ice. So, case closed, right? A giant ice cube in space? Well, not so fast. Scientists wondered if maybe a thick atmosphere could be acting like a planetary blanket, trapping heat and keeping all that water liquid. To find out, they had to somehow analyze its air. So how on Earth do you analyze the air of a planet over 1,000 trillion kilometers away? Well, the technique is called transmission spectroscopy, and the basic idea is pure genius. Instead of trying to look at the planet, you look at the starlight that's shining through its atmosphere, because the gases in that alien air leave a unique chemical fingerprint on the light. All right, let's break this down. As K2-18b travels in front of its star from our point of view, the starlight has to pass through its thin little layer of atmosphere. Now, different molecules in that atmosphere, things like water vapor or methane, they absorb very specific colors of light. Each molecule has its own unique fingerprint. So by analyzing which colors are missing from the starlight by the time it gets to us, we can figure out exactly what gases are in that alien air. The legendary Hubble Space Telescope was the first to give it a shot. Back in 2018, it picked up a signal that looked a lot like water vapor, which was a huge discovery. But there was a catch. In the narrow slice of light that Hubble can see, the fingerprint for water vapor looked almost identical to the fingerprint for methane. So was it an ocean world or just a gassy one? The data was just too fuzzy. The mystery was still unsolved.
So, while astronomers were waiting for a more powerful tool to come online, a team of scientists, led by Indian-origin researcher Niku Madhusudan, proposed a radical new idea. They weren't just looking at one planet, they were trying to define a whole new class of worlds.
They called them Hycean Worlds, a mashup of hydrogen and ocean. They had this theory that planets like K2-18b could have these deep, planet-wide oceans underneath thick hydrogen atmospheres. That hydrogen would act as a super powerful greenhouse gas, keeping the planet warm enough for liquid water, even if it's pretty far from its star. And get this, life on a world like that might not breathe oxygen at all. It might breathe hydrogen. It was a completely new way of thinking that just blew open the possibilities for where we should be looking for life.
Now, to test this wild new theory, we needed a much better tool. And in 2022, boy, did we get one. The James Webb Space Telescope. The leap in technology here is just staggering. I mean, if Hubble was like an old black and white TV, JWST is like a full-color, ultra-high-def, giant movie screen. It's so much more sensitive that it can clearly see the differences between those molecular fingerprints that just blurred together for Hubble.
So now you've got this new theory, and you've got the most powerful telescope ever built. What do? Well, you point it straight at K2-18b. The entire scientific community basically held its breath, waiting to see what secrets its atmosphere was hiding.
Okay, before I tell you what they found, we have to talk about one specific molecule. It's called Dimethyl Sulfide, or DMS. And it is a crucial piece of this puzzle. You see, here on Earth, DMS is overwhelmingly produced by life, specifically by tiny plankton in the ocean. It's literally the molecule that gives us that distinct smell of the sea.
And then, the results came in. JWST confirmed that the atmosphere of K2-18b had methane and carbon dioxide, just like the Hycean model predicted it would. But it also found something else, a faint but distinct signal of dimethyl sulfide, the potential smoking gun. Now you have to understand why this is so huge. Finding methane is interesting. It's like a whisper of a possibility, because geology can make methane too. But finding DMS? Oh, that's a shout. It is the strongest potential biosignature, the strongest potential sign of life that we have ever detected on a planet outside our solar system.
This is the moment the hype just exploded. But this is also where the story gets complicated, because in science, a shout isn't enough. You need absolute, irrefutable proof. And the case for life on K2-18b is still far from closed.
Here's why. The DMS detection we have right now is at what scientists call a 3 sigma level of confidence. That means there's a 99.7% chance the signal is real. That sounds amazing, right? But for a discovery of this magnitude, science demands a 5 sigma standard. That's a 99.99994% certainty. It's the difference between being pretty sure and being absolutely certain beyond any reasonable doubt. There's still a tiny but real chance that it's just a fluke in the data.
And it's not just the stats. There are other nagging questions. Could some unknown geological process be making DMS without any life involved? It's possible. And then there's this other missing puzzle piece. The team's models predict that if you have DMS, you should also have another gas, ethane, as a byproduct. Well, JWST hasn't found any ethane. So does that mean the DMS isn't real? Or does it just mean our models are incomplete? These are the points the scientific community is debating like crazy right now.
And you know what? This is the beauty of science. One tantalizing result doesn't end the story. It kicks off a dozen new ones. So right now, teams are working on all of this at once. You've got theorists trying to improve the Hycean World models. You've got lab chemists trying to see if they can create DMS without life. And of course, you've got astronomers booking more time on JWST to stare at K2-18b and try to nail down that signal to a 5 sigma certainty.
So let's go all the way back to that first question. Reality or hype? The truth is, it's a bit of both. The hype is justified because the potential discovery here is absolutely monumental. But the reality is that science moves slowly and cautiously. We do not have proof of alien life. But what we do have is maybe the most compelling lead in human history, a specific dot in the night sky to look at, and the perfect instrument to investigate it. The hunt on K2-18b has only just begun.